I'm going to work out two examples in this video from section 7.4 on trigonometric substitution. So I'm going to look at this problem here. Notice this problem involves a square root, and inside the square root you get a difference of two terms, each of which happens to be a perfect square in this case. So I just want to remind you from our handout and what we did in class before that we're led to trig substitutions partially by looking at the Pythagorean theorem. If we solve the Pythagorean theorem for a, b, or c, we get a square root, and inside the square root we have either the sum or difference of two terms, each being squared. So when we want to look at an integral like this, okay, it's kind of natural to view this as a situation where we're on a triangle, okay, where x is representing the length of one of the sides. In this case, since it's what we're subtracting from inside the square root, it happens to represent the hypotenuse, and the other term is 4 squared. We can let that represent either side of the triangle. Okay, could be the height or the base. In this case, I'm going to let it be the base length. We could let it be the other side. However, then we would be looking at what relationship would be between x and 4. If it was on the height, it would be cosecant. Instead, it's secant. Secant of theta is hypotenuse over adjacent, so you get x over 4, and that relationship tells us what to let x equal when we're making our trig substitution. Okay, we're going to let x equal 4 secant theta. Okay, now we take the derivative of each side, and we get that dx is 4 secant tangent theta. Okay, so we could go in at this point and replace x by 4 secant theta and dx by what it is, and then we could get the expression we want to integrate by using trig identities. However, we can get an expression for the square root of x squared minus 16 by using tangent. Tangent is opposite over adjacent, so we can read that out, which gives us that 4 tangent theta is equal to the square root of 16 minus x squared. That's maybe easier than working with the trig identities after we substitute and simplify. So going and plugging in here, we get 1 over x squared, which is going to be 16 secant theta squared, times we just computed that that square root was 4 tangent theta times the dx, which is 4 secant tangent theta d theta. After this, we're going to simplify, cancel out common factors on top and bottom. We get the 4's to cancel and the tangents to cancel. 1 factor of secant on top and bottom. We can pull the 1 secant 1/16th out, and we're left with 1 over secant theta. This should be 1 over secant theta, not just secant. But 1 over secant, the reciprocal of that is cosine. So that worked well. We end up getting an expression and we know how to integrate. And our derivative of cosine is sine. So we get 1/16th sine theta plus c is the antiderivative of the function of the expression we integrate with respect to theta. Now what we want to do is flip this back over to an expression involving x's, our original problem involving x. So we could just go up to our triangle. We want sine of theta. Well, there's our figure. Sine is opposite over hypotenuse. So what do we see? Sine theta is the square root of x squared minus 16 over x. So our antiderivative should be 1/16 times the square root of 16 minus x squared minus 16 over x plus any constant. And that's our answer. Okay, if you don't like that last approach about going back to the triangle, what you could do is take our identity, okay, and solve it for theta, which would give you theta would be the inverse secant of x over 4. And then you could look at 1/16 sine theta and replace theta by the inverse secant of x over 4. But then you would want to reduce that. You don't want to look at the inverse sine or sine of the inverse secant of x over 4. There's a way to reduce this if you remember from your pre-calc days. Okay, the inverse trig functions spit back angles. Okay, so the regular trig functions, you input angles and get numbers out. The inverse trig functions therefore have to return angles to numbers. So if we call this some angle like theta, okay, then theta would be the inverse secant of x over 4, and therefore secant would be of theta would be x over 4, and therefore looking at a right angle triangle, you could label it hypotenuse over an adjacent as x over 4. and that will lead us back to the same exact triangle we had before. So nothing would change. Okay, looking at a second example. Okay, this is number 4 from the textbook. We notice we also got a square root involved, a difference of two terms. What we're subtracting from has to be on the hypotenuse. In this case, it's 3 squared and gives us 9. X can go in either spot. I'm going to choose to put it on the height this time, so we'll work with sine in this case. In this case, the relationship between x, theta, and 3 is that x is equal to 3 sine theta. The derivative is 3 cosine theta d theta. To get the expression involving the square root, to replace that, we can also go to the triangle. What trig function involves the adjacent and hypotenuse sides? That's cosine. Okay, so cosine theta is the square root over 3, and therefore clearing the fractions to solve for the square root, we get that the square root of 9 minus x squared is just 3 cosine theta. Okay, now going back up, plugging that into our integral, x squared is going to give us 9 sine squared. Okay, in the denominator, replacing the square root of 9 minus x squared by 3 cosine squared, and then dx gets replaced by 3 cosine theta d theta. After that, we're just going to simplify our integrand involving theta and then integrate. Okay, so what do we see? We can cancel a 3 and a cosine from the top and bottom. We can pull the 1/9 out front, and we got the integral of 1 over sine squared. We know that sine squared, by definition, is cosecant squared. All right, so that's the same thing as integrating cosecant of theta squared. Remembering your derivative rules or antiderivative rules from Calc 1, the derivative of cotangent is negative cosecant squared, and therefore the antiderivative of cosecant squared is negative cotangent. So we get negative 1/9 cotangent of theta plus c. Once again, if we want to change this back over to x's, one way or the other, we're going to end up looking at the same triangle again that we have labeled. So going back up here, we see that cotangent, which is adjacent over opposite, we're going to get the square root of 9 minus x squared over x. Okay, and therefore our antiderivative is negative 1/9 times the square root of 9 minus x squared over x plus any constant.